Hello everyone. Today's topic is speed up large-scale MLDL offline inference job with Alluxio at Microsoft. My name is Binyang Li. I'm the software engineer from B, and my colleague Qianxi Zhang is the research software engineer from MSRA. We are working on Alluxio for several months to make it available in Microsoft internal production bed, and we also did some research work based on Alluxio. Today, I will focus on the engineer part. I will introduce how Alluxio is running in Microsoft and what's performance of the Alluxio in our internal bed. Here is today's agenda. First, I will show you the characteristics for offline inference job. For this part, you will know the data access pattern for offline inference job. Then, I will show you why it is challenging for us to run a large-scale inference job, and why current solution can't fit our demands, and what's the problem for the current solution. After that, I will show you the architecture and the optimization we did to running large-scale offline inference job. Then, I will show you the performance comparison with or without adopt Alluxio. Finally, I will show some future work we have done with the Alluxio community.
Let's come to the first part. In this section, I will introduce the characteristics for offline inference job. First, the scale part. For our offline inference job, each job contains about 400 tasks, and for each task, it reads different dataset and generates its own output. So there are no interactive between the tasks. And for each task, it reads about 2 to 3 gigabyte data and output about 3 to 8 gigabyte data. So the total input and output data is really huge. For the input data, it's about for one job, the input data is about 1 gigabyte, and for the output data, it's about 3.5 gigabyte. And to finish one job, it usually takes about 2 to 4 hours, so you can think about it as a non-running job. As for the data access pattern, for the inference job, the data access pattern is quite simple. It only reads the input data once and output the result to the edge blob. And the input data is a large file, and it reads the input data sequentially. It's not like the training job, which will read the input data once and once again for each epoch. And another data access pattern is we have a huge model, and for this model, every task in the job only read one model, so the model part is shared between all the tasks. Finally, I will introduce the infrastructure we use to inference our job. For the storage part, we use the edge blob and our storage system, and we use OpenPy. It's another open source project as our AI training platform. And for scheduler, we use HiveD. It's also an open source project. We use it to schedule our job to each load.
Why this job is challenging for us? First, because the number of total ingress and egress data is quite large. To process such large of data is easy to cause I/O failure. Previously, we used tools like Blockfuse to process such large of data, but Blockfuse has some behaviors which don't fit our demands. For example, when you use Blockfuse, you open file, it will download all files into local storage, and when you close the file, it will upload the total file to the Azure storage. But for our case, our single job contains about 400 tasks, and our tasks almost start at the same time. So at this point, all tasks download the file into local storage. At this time, it will cause high LPS as easy to hit the read limit of Azure. It's also same for the when you close the file. Because the tasks are almost same, so it usually finished at the same time. So at the same time, all tasks will upload the optical file to Azure, and you will also hit the read limit at this time. When you hit the Azure read limit, your job will fail. Then you need to retry the entire tasks to finish your job. That's quite noisy and also waste time. Another problem is when you use tools such as Blowfield. At the beginning, you need to download data, and when job is finished, you need to upload the data. At this time, your GPU is idle. You can't do anything. Although maybe there are other tasks is queued and waiting for the GPU time, but because this task occupies resources, so GPU cannot serve for other tasks. And because GPU is expensive, so it's wasting money. It's also wasting time. Here is a picture for our typical job. From this picture, you can see for each job, it contains about 400 tasks, and for this example, about 300 tasks already finished, and there are still about 80 tasks in running. It's a typical use case for our job.
Before I show you the architecture we adopt with the Alluxio, I will give you some information about our production bed. Here is the information. In our production bed, we use about 200 Azure low priority VM, and each VM has 4 GPUs. Please notice, the VM is low priority, so it can be preempted by Azure at any time, so the environment is unstable. But we must make our training platform be reliable and stable for our job and for our service. And for the version of Alluxio, we use the version 2.3, and we using the Kubernetes, which version is 1.15. We have running Alluxio for more than 6 months, and it looks quite good from our side. So then let's begin the architecture with the Alluxio. From this picture, you will see the architecture contains 4 parts. First is the job scheduler of our AI training platform. It's OpenPy and heavily. It's the original part. And then it's a training job, it's a storage system, and Alluxio works as a cache layer for our entire system. I will introduce an ideal case. We want to use Alluxio to speed up our info job or our training job. When a customer submits a job, it goes to the original part, it goes to our AI platform and job scheduler. Before the job starts to run, we want to send a command to Alluxio to let it load or let it prefetch data to the cache layer. And after it prefetch the data, our scheduler could schedule the job could start load, and because it already catch part of our catch the entire dataset, the training job will interact with Alluxio directly and skip the system storage and skip the storage system. It will only read or write through the Alluxio. Also, in the Alluxio part, we also want to customize some data placement policy to make it more efficient for the training and for the inference job. Here I will show you some optimization we did to non-Alluxio fade-out events. First is the deployment part. We saw many different deployment methods from community or from other companies. And the basic deployment method is deploy one fuse daemon in each node, and all jobs running on this node communicate with the fuse daemon to read and write data. We did adopt it this way because for our info job, it needs to read data than output data. For reading and writing, the configuration for Alluxio is quite different to make it more efficient. For example, for the reading, because some model file because all tasks need to read one model file, we want to catch the model file in the Alluxio, and we also want to catch the metadata for the read file to make it more efficient. So for the reading part, we turn the metadata on. We also want to enable the kernel cache. We also want to make the entry timeout to a large number to make sure the entry attribute not timeout. And for the output folder, we want to make because we need to write data to such folder, we need to turn the metadata cache off. Also, we need to customize the Alluxio config to make sure the write will write to the agent storage directly and not lost data. So we change the write policy to through in this case. To achieve this, we adopt the CSI-based deployment. You can see here is an example of how to use CSI. Because we have some configuration file to each CSI mount point. For this configuration, you can customize the mount option. You also can customize the Alluxio configurations, and you also can customize the mount folder inside the Alluxio. It's quite convenient for us. So from this picture, you can see for even for the one tasks or even for the one pod, you can provide two mount points, and each mount point means one fuse daemon process. So for one pod, you can create two fuse daemon to serve for it, and you can make each for one for read and one for write. And also for a different job, you also can create two fuse daemon and each for one workload. From this way, you can separate read and write mount options, and you can fine-tune the Alluxio config to fit read and write scenario to make it more efficient. And for each port, it's actually using different mount points, so it's actually using the different fuse daemon. So it means for each workload running on one workload, it has all fuse daemon. So if one fuse daemon is down, it only affects the workload which communicate with it. So it's not affect other workload running on the same node. It made our system more robust and more reliable. And another advantage for CSI-based deployment is that each job can mount to different paths, and this path can be controlled by admin. So admin can provide several such config such process value for the CSI, and for each job, it can only select one of the process value. So if admin doesn't provide such config, so then the job cannot mount this path. So it cannot mount other customers' path to modify the file and make our system more security, and we can do some access control based on this approach. Then we also did some optimization for the field client. For our case, is the inference job. So for the inference job, it need to output a large of data, and the data is really important for us and also important for the data scientist. To make the output more stable and for reliable, we did some enhancement for the field client. First is the flash enhance. For the real case, some customer gave us some feedback. It said to us he found the data is not he found the inference job is finished, but found the output data is not persisted into edge storage. Uh, we uh, we investigate this issue and find it because the Alluxio didn't implement the flash function in the field daemon. So when the job is finished, it will call flash function, but it return immediately. In some case, the data will not be persisted into the Azure storage. At this case, customer will lost data. Um, we solve this by implement the fuse function, and uh, we also contribute this fix to the community. And another issue for the Fuse client is the release function. Some customer find some customer need to post-process some the output data to do other experiments. Uh, but when they do the job, they open the data which output in the previous task, but find the but file cannot be opened, and we found some error message from the Alluxio log that said the file is uh, not completed. We investigate this issue and find that it's because the release function in Alluxio is release function in Fuse is async. Even in some case, you find the task is finished and you think something is okay, but maybe but because the close function is async, so maybe at this time the close operation is not finished yet. And but at this time, your job already finished. Your client is done. So the operation will be never be completed because the gRPC communication uh, is be dropped because client is done. We solve this issue by add some logic in the release function to some logic in the onMount function to make sure before the multiplier is unmounted by the customer, the all operations sent to by the client is done in the Alluxio server. We also contribute this fix to the Alluxio community. After adopt those two fixes, our service is become more stable and more reliable, and the user job failure rate is decreased after adopt the two fixes. Here, I also want to introduce an ongoing feature. It's called prefetch. Through this feature, we want to prefetch the data to the cache layer to the Alluxio before the job really start to run. And after adopt this feature, our workload don't need to wait the data to be retrieved from the other file system, and after start, it can be run immediately. I will show you the process we want to adopt. First, when customer want to submit a job to the OpenPy, OpenPy will know the job and it uses its job scheduler to queue its job. If there are already some tasks running on the cluster, the task need to wait for some time. But at the same time, OpenPy can send the prefetch command to the Alluxio. Then Alluxio can load the data through the Azure storage. So before the job really starts, the data already be loaded into the workload. Then OpenPy schedule the job to each workload. Uh, After this process is done, the job can start directly and don't need to wait for the data to be retrieved from the Azure storage. It could speed up our workload, and we already did some experiments. It shows a good result. Then I will show you some results. After adopt Alluxio, it indeed brings some benefit for us. This results from the real case in an experiment. You will see for after it's without Alluxio, and this is the system with Alluxio. So before we using Alluxio, you will see the job need to waiting some time to download data first. And after the task finished, it also need to wait some time to upload the data to the Azure. But after we adopt Alluxio, you can see we also need to wait some time to download data, but because we don't need to download the whole data, as I mentioned before, and if we use block fields, it need to download the whole data when you call open function. But in Alluxio, when you call open function, it does nothing. It did not say. It only download data when you call read function. So before at the job start, the we need to wait some time, but the time is quite short. Then the inference job start to running, and uh, and and to the end of job, you don't see it need to wait some time to upload data because the inference job will output the data during the inference. So because the job is quite long, it's more than 2 hours, so so data already persisted into a storage system during the lifetime of the job. So it stream the input and stream the output. It smooths the I/O request for our case. Also, Alluxio provides some advantages features such as read retry. Because Alluxio had read retry, so if your read request hit the Azure storage rate limit, it will not fill the job. You just need to wait for the next retry to then the job can continue work. And also from our real case experiment, we found after we adopt Alluxio, it decreased the I/O store and the performance improved around 18%. It gave a speed up for our inference job. And we also some future work we want to share with you. First is the and write retry. Alluxio already have read retry, but it doesn't have a write retry. So if for its workload is when you set one client need to write data, it set a write request to one workload, and the workload will process the data to the on-file system. But if the workload is down, the write will failure, and the client will go to failure, then the task failure. In our environment, because we use the Azure low priority VM, so workload may be done at any time. If that happens, our task will be filled. So we want to add the write retry to make our system more reliable and more stable. The next future of work is we want to adopt Alluxio for training job. Training job is more interesting, and training job usually have some special data access pattern, such as for training job it only has one huge data set, and for each epoch it's typically read the entire data set, and another for the another epoch it's also it reread the whole data set. It's reading and reading the data set again. And maybe in the sequential data access pattern, and maybe in the random data access pattern. So it make give us more challenges, and we need to propose a new data placement policy to fit the training job demands, and to make the training job more efficient to use the storage system. And for training job, and it's more performance sensitive, and it consume more GPU resources. So in the future, we want to adopt Alluxio for the training job, and to see the potential of the Alluxio, and to speed up the training job. Here are some resources which I mentioned in this presentation. Firstly is OpenPy. OpenPy is an AI trading or inference platform, and we use it in Microsoft to train and inference job. It's an open source project. It's a Kubernetes based, and if you have Kubernetes cluster, or if you want to try using Kubernetes to train your AI or AI workload, you can try this platform. It's open source. You can access it from GitHub. And then is the Hive. Hive is a customized Kubernetes scheduler, and it provides some advantage features such as its GPU topology event, and you can also use it to give different group different resources. It provides a concept such as virtual cluster, and you can try it to use it to schedule your job to a GPU cluster. The final is Alluxio CSI. We use it to mount paths to the job workload. That's all. Thank you for all your listening. Thanks.